In this video we're going to consider how we could construct what's called a slope field for a differential equation, which is kind of a numerical way of analysing what the gradient's doing and therefore what the function might look like. So it's a graph which displays the gradient of the relation between y and x at any point in the plane. So what we're going to do is basically draw a whole lot of little lines that show what the gradient of this relation might be at different points in the plane, and that might help us to get some understanding of what the graph actually looks like if we can think about its slope. So here's an example from the exercise. For the following differential equations, sketch a slope field graph and the solution curve for the given initial conditions using x between -3 and 3 and y between -3 and 3. Use calculus to solve the differential equation in each case. Alright, so this is asking us to do a bit of stuff, but what we want to focus mainly on is how do we draw this slope field. So we're told that dy dx is equal to 3x squared. Now that would actually be a very easy one to solve with calculus. Maybe if you take a moment you can see that that's the case. Solving that would give us a general solution, but we're also given some information here which would allow us to come up with a particular solution. So we're going to see if we can try and get that curve. Now it's given us that we want to think about x in the domain -3 to 3 and y in the range -3 to 3. Since our differential equation here is just dependent on x, really we could draw for ourselves a little table of values that considers for different values of x, what are the corresponding values of dy dx. So let's draw that up here, and let's go all the way from -3 to +3. So subbing in those values, let's just write it here as well, where dy dx is equal to 3x squared. Okay, well when x is equal to 0, 3 times 0 is 0. When x is equal to plus or minus 1, x squared is 1, so those would both be +3, wouldn't they? When x is -2 or +2, x squared is +4, so 3 times 4 is 12. And 3 squared is 9, so that's going to be 27 and 27. Okay, so because the equation there is an even power of x, we get a sort of symmetrical pattern there. So how could we now convert that onto our slope field graph? Well, let's sketch some axes here. So y and x. Put some. Now it doesn't really matter too much about putting on values of y here, because really what we're interested in is what is the slope doing at those values of x. But I guess, well, we'll still put some on because we want to see in this case that in fact changing y has no bearing, does it? So let me grab maybe another color to try and do this. So first of all, we've said over here that when x is equal to 0, the gradient, the slope is equal to 0. So not saying y is equal to 0, we're saying the slope is equal to 0. So at every point where x is 0, so here for example, slope would be 0. Here at y equals 1, x is still 0, so the slope is 0. So a slope of 0 means a horizontal line, doesn't it? So really all I'm suggesting here is wherever the function, which is the solution of this, y equals whatever, wherever that crosses the x-axis, its gradient is going to be 0. It's going to be horizontal at that point. And of course I could do this anywhere in between as well. It's not just valid for integer values, but we'll just do it at integer values to show those possible slopes. Now what about when x is +1 or -1? So when x is +1 or x is -1, we get a slope of +3. So let me try and represent that as, I'll sort of show it like that, even though that's probably closer to +1, but I've got to try and compare it to some others as well. So likewise, I'm going to go up here and I'm just going to say, well, at any value of x equals 1, wherever the curve crosses x equals 1, the sort of imaginary line, the slope is going to be +3. And the same at -1. So these ones here can all have the same value of slope. So they're all meant to be roughly the same. I haven't done a brilliant job with that. Then I could say when x is +2 or -2, the gradient's going to be +12. Okay, well, +12 is a pretty steep positive line. Having said that, it's not as steep as +27, so I want to still give myself a little bit of scope to show the difference. I guess as much as anything here, I'm trying to show a relative difference between a slope of +3 and a slope of +12, and then a slope of +27. +27 is a slope that's very close to vertical, really, isn't it? So these lines here are almost as good as vertical. All right, what have I got? So I've got a graph here which is showing me what the gradient of the solution of this differential equation is doing. So if I sort of start over on the left-hand side of the domain, it's got a steeply positive gradient over here. Then it gets kind of less positive as I come around, then a bit less positive, and by the time I reach x equals 0, wherever it's crossing the y-axis, its gradient is 0, and then it starts getting positive again, and then more positive and more positive. So really it would be something like a cubic, wouldn't it? Going positive, less positive, less positive, 0, and then positive, more positive, and more positive again. And it's never negative. So one of the things I know about the solution to this differential equation is it never turns around and starts sloping downwards at any point. So I know its general shape is kind of a cubic like that without a turning point, which has a point of horizontal inflection somewhere along there. But if I use my extra bit of information, which is that y is equal to 0 when x is equal to 1, so let's write that over here. Also given y equals 0 when x equals 1, so that would be that point there, wouldn't it? The point 1, 0. Alright, so I want my curve to come down through there and cross at that point. So let's have a go at drawing something which slopes sort of down here and then through there and then down there again. So the curve we would expect is going to look something roughly like that. So that's the solution to dy dx equals 3x squared. Now I'll show you in a moment how you can do this on your graphics calculator, but it did also ask us to use calculus to solve the differential equation. So let's do that as well. Dy dx equals 3x squared. So we're just going to integrate with respect to x, which is x cubed plus c. And if we substitute in the point we were given, which is 1, 0, then we get 0 equals 1 plus c. C is -1, therefore y is equal to x cubed minus 1. Okay, well that was pretty close to the curve that we drew there, wasn't it? Going down through there and intersecting the y-axis at -1. So how about using our graphics calculator? Well, what we want to do is grab a graph here, and then in our menu we just want to change our graph type to a differential equation, and then it's got y1 dash, so the derivative, that's basically dy dx for the first function, and we're only going to enter one, so it's just going to be 3x squared, and also we're given that when x is 1, y is 0. There's the graph of that function for us. So yeah, a whole lot of points down there. You can see the slope field that's been drawn, and basically as soon as we get very far out here, all these lines are almost vertical, aren't they, because the slope is so steep. But we can see that curve there, and we can see the initial condition, which is that point there where it's crossing the axis.